Hello everyone. Okay, so this is going to be a lesson about related rates for Calculus 1. If you've been following the lesson so far, you know that we've been learning how to differentiate a lot of different functions. And this is the point in the course where we're going to start seeing applications of that. So I think of Calculus 1 as being divided into a few different portions. At the beginning of the semester, we had lessons about limits, and that was our first main topic, was limits. And our second main topic was methods of differentiating functions. Now I feel like we begin our third big topic, which is applications of the derivative. So if you know those derivative rules, then you're ready to go. And, applications, some of them are going to be applications to real life, which might mean some word problems. And some of them are going to be applications to math itself. Like, what can the derivative tell us about a function in a mathematical sense? But we're kind of past the point of adding tons of differentiation rules, and we're moving on to let's apply those rules and see what they can do for us. Okay, let's go ahead and look at some related rates. All right, so what are related rates? Well, the answer to that is it's a certain type of word problem. And, most of this section is just going to be example problems because the best way to demonstrate these is just to show you some of them. We're going to be applying what we've learned to a certain type of word problem. Before we do that, I'll tell you a few key ideas. So remember that the derivative measures a rate of change. We should all know what that means by now, but the derivative is telling us the slope of the tangent line, and when we originally introduced the derivative, it was because we were trying to measure the slope of a curved line and figure out, what is the steepness of a curved line. Visually, that's what it looks like, but you can also think of it just as how fast is the function changing. So it's the rate of change for a function. In fact, with implicit differentiation, we learned that we could even see the rate of change of something that's not a function. Y doesn't have to be a function of x. Anyway, in real life, some rates of change are easier to measure than others. And we'll see what I mean by that when we get to some example problems. But, think of rates of change that you might encounter in real life. Some of them might be, uh, velocity. Some of them might be how fast is your car moving. Some of them might be acceleration. What's the acceleration of your car? I think that between those two, I would say it's probably easier to measure the velocity of your car than it is to measure the acceleration of your car, right? So, and we're going to see other rates of change besides just that. Now, what we want to do is we want to compute the rate of change. In parentheses, I'm going to say derivative of one quantity by using what we know about the rate of change derivative of some other quantity. We want to compute one rate of change by using what we know about some other rate of change. And that's why it's called related rates. There's going to be two rates of change that are related somehow, One of them might be easier to measure in real life. So we want to have one that we can easily measure and then use it to inform us about the other one that's related to it. So let's get into our first example. And I'll be doing the first couple of examples for us to kind of talk us through it, and you'll see what kind of strategy you use on these word problems. So, first example. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon? Increasing when the diameter is 50 centimeters. All right, we've never seen a problem like this before in this class, so let's talk about it, but I'll give you a chance in case you're copying that down. Now, I could review, general techniques for how to deal with word problems, but I think that you've seen that before in algebra classes and pre-calculus classes. You know with word problems that you want to read the problem carefully. You want to maybe read it twice. Organize the information that's given and figure out what information we are looking for. All of the usual things. You want to look at maybe the units that are in the problem. I see centimeters and centimeters, okay, and we're talking about rates of change, so this was cubic centimeters per second, so that tells me the unit of time that we're using. All right, let's get started on solving this, but I'm going to break it down into a few steps. First of all, I'm going to say what is known. Let's just extract what is known. Now, in related rates problems, there are going to be generally two rates of change, one that we are interested in and one that we are given. Are we given a rate of change here? Yeah, 100 cubic centimeters per second. That's the rate of change of volume. In fact, I'm going to underline the word volume. The problem doesn't underline stuff for us, but I'm going back to the problem and I'm going to underline the volume rate of change is 100 cubic centimeters per second. Let's write this. What is known is the rate of increase of volume is 100 cubic centimeters per second. And we assume, from the way this is phrased, we assume that that's consistent. Like, as air is being pumped into the balloon, it's a consistent 100 cubic centimeters per second. Maybe we have some tank of air and it has a little nozzle on it and it has a little meter, and we can tell from the little meter that we are pumping air in at consistently 100 cubic centimeters per second. What's the unknown rate of change that we're looking for? It says, how fast is the radius of the balloon increasing? So, all right, how about I underline radius? This seems to be a problem about volume and radius. So what's unknown is the rate of increase of radius. Oh, there's some more, though. There's some more to this. It doesn't just say how fast is the radius increasing. It says when the diameter is 50 centimeters. That seems like that might be important. So let's write that here. When the diameter is 50 centimeters. I'm thinking to myself, if I try to picture this in my head, I imagine a sphere that's expanding and the volume's increasing, the radius is increasing, the diameter is increasing. And it does seem like the answer to how fast is the radius increasing, it depends on what moment in time are we looking at. At first the radius expands quickly, but then as the balloon gets larger, I probably should have had a balloon here to demonstrate this. As the balloon gets larger, it seems like the radius rate would not be as high as it was at the beginning, right? At the beginning, it like rapidly expands and then it kind of tapers off a little bit. Anyway, so yeah, that's why it has to tell us when we are interested in looking at the radius. It could have given us maybe a t value, but it didn't give us a t value. It gave us when the diameter is 50 centimeters. And then you might say to yourself, wait a second, diameter. Let's be careful. Diameter is not the same as radius. So let's say, in other words, when the radius is 25 centimeters, right? Because the diameter is twice the radius. And we'll write this as, what we're looking for. And then we'll see which one of these do we want to use, diameter or radius. I have a feeling we're going to want to use the 25 because this is about the rate of change of radius. The diameter feels like it was in there to throw us off. So, what do you think is next for this? It's a word problem. Let's introduce variables. Let's give these things names. I think we should let V be volume. I think we should let R be radius. I think we should let T be time. Now, if you wanted to choose other letters, technically you could, but I would suggest that you use letters like this. It's going to help organize the information. It's going to make it easy for you to understand and for me to understand that you're using V for volume, R for radius, T for time. If we had something like area, I would use A. Try to use letters that make sense. And I think that maybe all of these problems, either all of them or probably all of them or almost all of them are going to have T for time. Because we're interested in real life things that are changing as time passes. All right, now the things that we said above, the rate of increase of volume is 100 cubic centimeters per second. We can rewrite that in terms of these letters. Rate of increase of volume. What's another way to say that? Rate of increase of volume. How about dV dt is 100 cubic centimeters per second. Rate of increase of radius. Another way to say that is dr dt. And that's the one we're looking for. In particular, when the radius is 25 centimeters. So we've organized all the information, what's known, what's unknown. We introduced variables, and then we expressed what's known and unknown in terms of these variables. We know this rate of change. We want to find this rate of change at the moment when the radius is 25. So far, I would say it seems like standard word problem stuff. Here's where we get into the new part of it. In these problems, at this point, you want to write a formula of how these variables, I'm going to put in parentheses, V, R, I'm just going to say V and R. V and R are the two things that we took derivatives of. So these are the main things of interest. I even underlined them in the problem, volume and radius. So write a formula for how these variables relate to each other. How are volume and radius related to each other? There's one thing that's in this problem that we haven't used yet. It says that the balloon is a sphere. So the volume of a sphere is related to the radius by the following formula. V equals 4/3 pi r cubed. That's the volume of a sphere. Okay, so a couple of things. Right away, you might be saying, oh, is that a formula we need to memorize? So listen, in this section, you're going to need to know some formulas. I'll say this is one that the volume of a sphere is probably one that I would not require you to memorize. Maybe I would provide it. You could look up formulas like this in the front flap of the textbook if you need to for a homework problem. I do think that there are certain ones that I would expect you to memorize. I would expect you to know the formula for the area of a circle. I would expect you to know area of a triangle, area of a rectangle, volume of a cube. What else? Pythagorean theorem, similar triangles. Some of these things are going to come up in examples, and some of them I will want you to know the formulas. But volume of a sphere doesn't come up all that often. So if you didn't know this formula off the top of your head, don't feel bad. You probably did know that there is a formula for the volume of a sphere and that it would involve the radius. Well, okay, here it is. So this is a formula of how these variables are related. So what's the calculus part? We are going to differentiate I guess I should say differentiate implicitly, because we're going to differentiate both sides of this. What is the variable with respect to? What variable? Is there an x? There's no x in this problem, right? We've not mentioned x at all. The variable that we're going to differentiate with respect to is time, t. So we want to do d dt of both sides. Do d dt of both sides. So the left-hand side becomes dv dt. The right-hand side, what happens when I do d dt of the right-hand side? 4/3 is just a constant. That can stay. Pi is just a constant. Here, I'll write it out. All right, we'll do it now. Do you see that the 4/3 is a constant? It can be pulled out front. Pi is a constant. It can be pulled out front. So really, it's just d dt of r cubed. And because we're doing implicit differentiation, this is going to be 3r squared, but then a dr dt is going to pop out, right? Let's write it. 3r squared, and then a dr dt pops out. I think we could probably simplify this right-hand side a little bit. I see a 3/3. So let's clean this up a little bit. dv dt equals, instead of having a 3 and an over 3, let's say this is 4 pi r squared dr dt. All right, let me highlight something for you. So this tells us how V and R are related. This tells us how the rates of change are related. That's why it's related rates. The rate of change of volume and the rate of change of radius are related by this formula that we just found. What are we trying to do in this problem? We differentiated implicitly. Usually when you do implicit differentiation, then you solve for something, right? Okay, I want to remind you, what are we trying to find? This. from our previous page. We're trying to find dr dt equals question mark when r equals 25. So we're going to solve for dr dt. That's the one that we want to know. So rearrange what we have above, divide both sides by divide both sides by 4 pi r squared, and I guess you get 1 over 4 pi r squared dv dt. How does that look? We found dr dt in relation to these other quantities. Now use our known information. So dr dt equals 1 over 4 pi. We know the radius that we're interested in is 25. And we know dv dt is always 100. So I put in the 25 and the 100 for r and dv dt. This is a number. This just simplifies to a number. Can we do this by hand? Yeah, I think we can. I know that 100 is 4 times 25, right? So if 100 is 4 times 25, you can cancel the 4 and one of the 25s, and you wind up with 1 over 25 pi. So I'm going to write the answer. We found it. When the diameter is 50 centimeters, the radius is increasing at a rate of 1 over 25 pi. What kind of units should we say? Centimeters? How about centimeters per second? Because it's a radius. Radius is measured in centimeters, but how fast is the radius changing? Centimeters per second. By the way, in case you're curious, I found this with a calculator. I think we could stop here. We're done with this problem, but I went ahead and found it as a decimal anyway. I don't know why. We don't need it as a decimal. There it is. It's a very small rate of change. So I'd like to quickly review what we did here. And you might be saying, oh, geez, this whole problem took us forever. Is every problem in this section going to take forever? Well, no. I mean, what wound up happening here was it took a long time because it was the first time we've done one of these problems, and I wrote a lot. We're going to be able to do this without writing so much. So let's just quickly go back and review. Here's the problem as it was given. Maybe we underlined the terms that we thought were important. Volume and radius is really what this problem was all about. I think another word that wound up being important was this word, spherical, because we had to use the formula for the volume of a sphere. So if there's some kind of shape involved with your problem, you might want to identify that first. All right. We wrote what is known, what is unknown. We introduced variables, and then we put it in terms of these variables. And I think in the future, I might skip writing these parts up here. What's known, I wrote it out in words. What's unknown, I wrote it out in words. We could just skip right to the introduce variables part. Because we did write, here's what's known, here's what's unknown. So, all right, you do this kind of thing for a related rates word problem. Then the next step was write a formula of how the variables are related. This is where you use something like what shape is mentioned in the problem. This problem had a sphere. I think the next problem is going to have a circle. So whatever shape you're dealing with might have a formula associated with it. Rectangles, triangles, spheres, circles, whatever. This is the formula for this problem. And then we did d dt of both sides. Got to here. And then we solved for the unknown rate of change. And you have to figure out which one are you solving for. Well, by this point in the problem, you've already written down what was known and what was unknown. So you solve for the one that is unknown, and then you plug in the known information at the very end to get this into a number. So it's not that bad. It just looks like a lot of writing. The only calculus part we really did was the implicit differentiation, right? Okay, let's do another one. This time I won't write so much, now that I think we get the idea of what these problems are all about. Suppose oil spills from a tanker and spreads in a circular pattern if the radius of the oil spill increases at a constant rate of 1 meter per second, how fast is the area of the spill increasing when the radius is 30 meters. Okay, there's the problem. I'll give you a chance to see that. Okay, so we read the problem carefully. We think, what are the most important words in this problem? Like, what is this problem really all about? It says, in the end, towards the end of the problem, it actually asks you the question, which is, how fast is the area of the spill? I'm going to underline area. How fast is the area of the spill increasing? So it looks like this problem doesn't really have the word rate. I guess the balloon problem had the word rate. Oh, it does have the word rate. It's right there anyway. Yeah, it's here. But yeah, we're interested in the rate of change of the radius and the rate of change of the area, right? Those are the two things. One of them it says rate, one of them it just says how fast. That's the same idea. How fast is it increasing? That is, what is the rate of change? Circular. Circular seems like it's going to be important. It says when the radius is 30 meters. So this says radius and this says radius. So I don't think there's any kind of trick about us having to convert diameter to radius. Another quick thing I'll check, though, is the units. This says meters and this says meters. So we don't really have to convert units. It's already in the same units. I guess that's something to be aware of. If you get a problem and it says like meters and centimeters, you might have to convert, but they're already both in the same units. Let's get started. Solution. Let's let A equal the area, R equal the radius, T equals time. I said we were going to write a little bit less this time, so we're just jumping right into the variables. I think those are good names. And then what is known, we know the rate of change of the radius, dr dt, is known to be 1 meter per second. And I'm just going to write 1. I'm not going to write the units here. I think as long as we write units in the final answer, that's all that I really care about. Let's say in the middle of the problem, we don't have to write units. What do we want to find in this problem? In terms of these letters, we want to find dA dt. when r equals 30 meters. But let's write r equals 30. So in a moment here, I'm going to have to move the page and move the problem away, but I think we've all got the problem by now. What do we do at this point in a related rates problem? We write a formula for how these quantities are related to each other, A and R. How are A and R related? They're both parts of a circle, the area of a circle and the radius of a circle. In this problem, I want to use A equals pi r squared. That's not given in the problem, but the word circle tells me I need to use the formula for the area of a circle, and you should know this formula. Now, what do we do with it? Differentiate. Differentiate implicitly. We want to do d dt of both sides, right? So now I think I'll move the other page away. We've got our formula, d dt of both sides, so the left-hand side is dA dt. The right-hand side, pi is just a constant. Don't forget that. Pi is just a number. It's around 3.1. So what's the derivative of r squared? It's going to be 2r times dr dt. So let's write 2 pi r dr dt. The dr dt pops out because we did implicit differentiation, and the chain rule tells us that a dr dt pops out because r is a function of time. A is a function of time also. And, you know, if this formula had something more complicated on the left side, we would have to deal with that with the chain rule. But it just says A, so we just get dA dt. All right, this is a formula for how the rates are related. And now we want to say, all right, which one are we looking for? We're looking for dA dt. This is the point in the problem where we would solve for dA dt, but we're lucky because it's already in that form. dA dt equals this other stuff. So there's no rearranging that I even need to do. Let's use known values. dA dt equals 2 pi 30 times 1. See, that's not bad. That equals 60 pi. That's what we were looking for. And in the end, this is the answer, so I'm going to put units. Let's think about what this is. This is the rate of change of area. Area would be measured in square meters, right? So how fast is the area changing? Meters squared per second. That's it. That's the whole problem. So we didn't write so much this time. This time it took up, for me, about a third of a piece of paper. Not bad. This is probably about the amount that I would write for a related rates problem. Now, granted, the formula for this one, the area of a circle, is relatively simple, so there weren't that many steps, but still, you could typically write this amount. So I'm going to give you a problem to try in a few minutes, but before we do that, I want to say some just general things about related rates problems, some things to watch out for, and some notes, okay? Let's just say remarks. Got a few things. All right, first of all, the first one is a warning. A common mistake is putting in the known values too soon. Don't put these in until after you differentiate. So that's my first remark. You know that in both problems that we did, we had some known numbers that we were able to plug in. Don't put them in too soon. That's my warning. I just want to show you in this problem, when did we put the known values in? It was like pretty much the very last thing we did was we put those numbers in, and then maybe we simplified, but we put the numbers in at the very end, okay? You don't want to put them in here. The 30 and the 1, like let's say the 30, for example. What if you had put the 30 in here? You say, oh, r equals 30. What if I put a 30 in? Would that work? If I had put the 30 in now, at this point, 30 squared is 900. So I would have a formula that says a equals pi times 900. Then I would try to differentiate it. What's the derivative of pi times 900? It's 0 because pi is a constant and 900 is a constant. So I would get 0 as my answer. And that would be wrong because I put in the 30 too soon. So don't put in the 30 or the 1 until the very end of the problem. Okay? In general, I would say that if you do a related rates problem and you get an answer of 0, I would go back and double check and triple check. I'm not saying that it's impossible to get an answer of 0, but it seems to me like it would be very rare or unlikely to get an answer of 0, and it might indicate that you did something wrong. It might be something wrong. Other remarks. Draw a picture. Draw a picture if it will help. So the problems that we were doing, I was kind of envisioning in my head a sphere that was expanding or a circle that was expanding. And I didn't draw the sphere or the circle. What if we had a problem that was like a cube or a rectangle or a triangle? You know, some of them you can visualize in your head. Sometimes a picture would help. I'm going to say especially for triangle problems. We didn't do any of those yet. But I think if you get to any that you think there's a triangle involved, drawing a picture is going to help. You can label sides or whatever. I'm going to say use... So in the recommended textbook, there's a reference page in the front of the book for some of the more obscure formulas, like the volume of a cone, etc. On an exam, you won't be allowed to use that reference page. So either if it's an obscure formula, I would give it to you, or I would give you a problem that uses some of the less obscure formulas that you should know. You should know, you know, do I need to list these? All right, fine. Area of a circle, rectangle, triangle. You should know those formulas. I guess I could say volume of a cube. The Pythagorean theorem could actually come up in a triangle problem. And the method of similar triangles could come up in a triangle problem. You could also, I suppose, get something that's like a rectangle with a circle attached to it or something like that. But as long as you know these ones, you should be able to get by. All right, last thing on my list of remarks is be careful about units. So 1 meter equals 100 centimeters, etc. In case you have to convert within a problem. We didn't have to for these problems we just did. But, you know, if you are given something where a problem tells you something about meters and something about centimeters, don't just use those numbers. Convert both of them to the same units. Convert both to meters or convert both to centimeters, and then continue with the problem. If you have something that's with inches and feet, there's 12 inches in a foot, convert, right? If you have a problem that involves both, convert before you do it. I guess I'll also say, I said that was my last thing, but I'm adding one more. Be careful about diameter or radius. You know, in that very first problem we did, we had to convert diameter to radius. The diameter is twice the radius. If it says the diameter is 50, you might want to say, oh, the radius is 25. So that's a good whole big list of remarks. I think you're ready to try a problem. The problem I'm going to give you, I'm going to tell you that for this next problem, I probably would not draw a picture. I say draw a picture if it will help. I do not think I would draw a picture for this one, so don't worry about that. Wait till I write the whole thing, because there's going to be two parts to this question. The voltage, V, in volts. Current, I, which is measured in amps. And resistance, R, which is measured in ohms, of an electric circuit. Are related by the equation V equals IR. There's going to be a part A and a part B. All right, so far I feel really good about this problem because I'm looking at it and I'm thinking, wow, this is already giving us a bunch of info. This is giving us the variables we should use. It's giving us an equation that we can use. Part A says find an equation relating dr dt to dv dt and di dt. Part B, suppose V is increasing at a rate of 1 volt per second, and I is decreasing at a rate of 1/3 of an amp per second. Find the rate at which R is changing when V equals 12 volts and I equals 2 amps. All right, so I'd like you to pause the video, take a few minutes, and give this a try. All right, so for this problem, we don't even have to do the part where we introduce letters because it already gave us V, I, and R. The equation of how V, I, and R are related is not something that you would find in the front flap of a textbook, of a calculus book. This is more of like an engineering question. This is like an engineering problem. So pretty cool that we get to see an application there. Part A, I know we're going to use V equals IR. And I think that to get from V, I, and R to their rates of change, I think we want to do ddt of both sides. ddt of V equals ddt of I times R. The left-hand side is easy. The left-hand side is just dv dt. What do we have to do on the right-hand side? What do you think? I'm going to use the product rule. So we have a product of two things. And by the way, I is a function of time, R is a function of time. So product rule says you take the first function times derivative of the second one plus second function times derivative of the first one. So now we found this formula for how the three rates of change are related. dv dt equals this stuff. But I guess the problem said to find an equation for dr dt relating to these other two. So we want to solve for dr dt. Right? We'll rearrange it. By the way, don't plug in any of these known pieces of information. Don't put in the 1 or the 12 or the 2. We said don't do that too early. So we're not doing that at all in part A. I guess I would get dr dt onto one side of the equation and everything else onto the other. And now let's do, should we divide everything by I? Divide everything by I? Yeah, we could do that. I think instead I'm going to multiply by 1 over I. And that's what I get for part A. That is an equation for how dr dt is related to the other two rates of change. And we need that to help us with part B. Part B gave us some information. Let's write what was given. So we're given dv dt equals 1. We're given di dt equals, let's be careful here. Is it 1/3? It says I is decreasing at a rate of... We haven't really seen the word decreasing today until now. When a rate of change is decreasing, it means it's negative. Okay, so increasing is a positive rate of change. Decreasing is a negative rate of change. We're also given v equals 12 and I equals 2. So that's all the stuff we're given. We know v equals IR. You know what? Let me explain where I'm headed with this, okay? Let's just put a dot. We'll come back to that in a second. What are we trying to find? It says find the rate at which R is changing. So we want dr dt equals question mark. We have a formula for dr dt. Are we ready to just put in all the information? So let's look at the 4 pieces of information we're given and imagine that we put them in. Don't put them in yet, but just like say, all right, if I put in dv dt as 1, put that in there. If I put in di dt is negative 1/3, put that in there. If I put in I equals 2, put that there. What are we missing? What about R? Do we know what R is? It wasn't given in part B. It didn't tell us a value of R. In fact, it told us a value of V, and it might be like, you might be thinking, how am I going to use the 12? V doesn't even appear in this equation by itself. R does. So it seems like we were given the wrong thing. It seems like we were given V, but what we really need is R. We're going to use this equation, V equals IR, so R can be found. Sometimes you have to do something like that. We found it pretty quickly, right? So don't forget, you can go back and use whatever information was given in the problem. We were given that V equals IR, so if you know 2 of these, you can find the 3rd one. We knew v and I, and we used it to find r. R is 6. So now I'm ready to find dr dt by plugging in all the known information, because we already differentiated in part A. So 1 over 2 times 1 minus 6 times negative 1/3. And we're going to simplify this and see what number this equals. See where the 6 came from? Came from that. All right, so this equals 1/2 times, what's going on here? 1 minus 6 times minus 1/3. 6 times a third is easy. We could do a third of 6. And then it's a negative and a negative, so it becomes a positive. So 1 plus 2. 1/2 of 1 plus 2, I'm going to say my answer is 3/2, or 1.5. And I'm going to put a box around it, but I want to think, what's the units? What's the units? This is the rate of change of R, and the problem told us that R is measured in ohms. So I'm going to say ohms per second. And that's a good answer. By the way, we answered it, but I'm just going to say the answer that we got is positive. So it means the resistance is increasing at this rate. Just put that in parentheses. It's just kind of, we did get a positive answer. The question said find the rate at which R is changing, and I'm just telling you we found that it is increasing. I suppose in an actual engineering application, you might need to know if things are increasing or decreasing and what's the rate. Okay, so we've seen a good number of examples now of some different types of problems. One involved a sphere, one involved a circle, and then this one didn't really involve a shape at all. But that was okay because we were given the formula V equals IR. So I've got another one to show you. This is going to be our last one for today. A ladder 10 feet long rests against a vertical wall if the bottom of the ladder slides away from the wall at a rate of 1 foot per second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So I'm going to walk us through this one. I'll give you a chance to look at that. Try to figure out if you can picture this in your head. All right, so I think we should draw a picture for this one. I think we're trying to envision this ladder against a wall. The bottom of the ladder is sliding away from the wall, so the top of the ladder must be sliding as well. And there are rates of change associated with both of them. Let's draw a picture. I think a picture will help with this. So I'm gonna do kind of a side view, and we'll assume that the wall is straight up and the ground is flat. So let's say this is the ground, and let's say this is the wall. And let's draw a ladder leaning against it. Well, we don't know what angle it's kind of making with the wall, right? But that's okay. We're just going to draw a ladder leaning against, and it doesn't have to be, we don't have to like get out a protractor and measure an angle or anything like that. Just side view of a ladder. I know the ladder is 10 feet long, so maybe I'll label this 10. The length of the ladder is not changing, right? I mean, the ladder is moving, but it's still a 10-foot ladder. So, the wall's a rectangle, but look at this. The ladder makes a triangle with the ground and the wall. So this is going to be a triangle problem. Not only that, let's zoom in. Not only is it a triangle, it's a right triangle. Look at this. This is a 90-degree angle here, isn't it? If the ground is flat and the wall is vertical, then this is a 90-degree angle. Now, is there anything we can label on this? I think we probably should give these side lengths a name. The lengths of the sides of this right triangle. The hypotenuse is already labeled 10. What about the other sides? What do you want to call them? The bottom and then the side one here? We could call them A and B if we want, because sometimes you think Pythagorean theorem has an A, B, and C. I don't know if we're using the Pythagorean theorem or not, but I think of a triangle as A, B, C sometimes. Or we could call it X and Y, because it's sort of a horizontal and a vertical. I think that's what I'm going to do. I'm going to call this one X, and I'm going to call this one Y. Now, what's happening as time passes? As time passes, we are told that the bottom of the ladder is sliding away from the wall. So this point right here is moving in this direction at a rate of 1 foot per second. Can you picture as this slides in this direction, the top of the ladder is going to slide downward? That makes sense, right? And then eventually, after enough time passes, the ladder is going to be completely flat on the ground. This point is going to move to the left. This point is going to move all the way down, and the ladder is going to have slid all the way down and just be flat. Okay, let's zoom out again, and let's write some stuff to the side. We gave our things some names like X and Y. So let's talk about what is known and what's unknown. I'm going to say that we are given that dx dt is 1 foot per second. You see why I'm saying that? Because I labeled this side length as X, and this side length of the triangle is growing. As this goes to the left, X becomes larger. Doesn't it seem like Y is going to become smaller? Anyway, we want the rate of change dy dt when x equals 6. So what's a formula for how x and y are related? What do you think? I already spoiled it for us. The Pythagorean theorem. The Pythagorean theorem is a formula for how x and y are related to each other. We know that x squared plus y squared equals 100. Because that would be the hypotenuse squared. So that's good. Let's differentiate both sides. Both sides. I'm continuing it over here, but we're taking that formula and doing d dt of both sides. When I do d dt of the left, I get 2x dx dt plus 2y dy dt. equals 0. We could simplify this a little, right? Let's just divide everything by 2. Let's cancel the 2's. Divide left and right side by 2, and you just get rid of those. So that's good. What are we trying to find? dy dt equals question mark. So can we solve for dy dt? Let's get this onto one side of the equation. I made a mess of this. Let's rewrite it. Minus x dx dt. How does that look? We got rid of the 2's and we rearranged a little. We're trying to solve for dy dt. So let's divide both sides by y. So we get negative x over y times dx dt. I haven't plugged in any of the known values yet. Now, let's take a look at everything that's on the screen right now and think about it. What are we looking for? dy dt equals something when x equals 6. Oh, and we also know that dx dt is 1. So, at this point, it feels like I could put in, we already differentiated. So, can I put in 1 for dx dt and 6 for x and get an answer? There's one thing missing, isn't there? What are we going to plug in for y? You could look back up at the problem and say, did they give us y somewhere? No, they only gave us the 1, they gave us the 6. The ladder's 10 feet long, but that's not y. So they didn't give us y. So it's kind of like that previous problem where we had VIR and we didn't really know what R was. We need to find y now so we can put it in. How do you think we're going to find y? Use the formula that you already wrote for how x and y are related to each other. So we know that x squared plus y squared equals 100, and we know that we are interested in what's happening when x is 6. So 6 squared plus y squared equals 100, and we can find y from this. So y squared is going to be 64, so y is going to be 8. Can y be negative 8? It's a side length of a triangle, so I know that it has to be positive. So now I'm ready to put in values. Put in known values. I get dy dt equals negative 6 over 8 times, what's dx dt? It was 1. So I wind up with negative 3/4. Put a box around that. And what unit should this be? This should be feet per second because it's a length that's changing over time. All right, so we did it. So that was an example of what I call a triangle problem, a related rates triangle problem. We had to use the Pythagorean theorem in this one. The other type of triangle problem you could see, I guess you could see one that involves like the area of a triangle changing, or it could be something where you have to use similar triangles. So why is this negative? Let's just do a quick reality check. Does it make sense that this is negative? Looking back at the picture, yeah, I think it does, because I think as time passes and the ladder slides, I'm expecting the shape of the triangle to change to where x is becoming larger and y is becoming smaller. So y is decreasing, so its rate of change is negative. So it does make sense. All right, so that was our section on related rates. We learned about a new type of word problem that is basically an application of the derivative. Like, this is something that derivatives can be used for. And you could see that there are some real world questions here, engineering and physics and just, things about shapes that are changing size as time passes and things that don't involve shapes, like that one engineering problem. So I guess that's going to be it for this lesson. In the next lesson, we're going to jump to a different application of the derivative and see something else that it can be used for. All right. So take care, everyone, and I'll see you next time.